Hello everybody. In this video we are going to talk about the definition of what a polygon is and how we can measure the interior angles. In the next video we will talk about the exterior angles. Before we can start doing some calculations, we have to agree on the definition of a polygon. And a polygon is a closed figure formed by 3 or more line segments. The reason it's 3 is if you only have 1 or 2, you're not going to get a closed figure. The lines cannot curve and they cannot cross. So they cannot curve, you cannot have curved lines in a polygon, and they cannot cross over each other in the types of polygons that we're doing. If you look up some definitions, they will include ones that cross, but the rules that we learn do not apply to those types of figures, so we tend to exclude them from our definition. Now, beyond polygons, we also have a regular polygon. Regular polygons are polygons that are both equilateral and equiangular. Remember, equilateral is when all of the sides are congruent, and then equiangular is when all of the angles are congruent. So in a regular polygon, the sides are all going to be congruent and the angles are all going to be congruent as well. Polygons also can be concave or convex. Now, the definitions of these words tend to be more complicated than what they would be if we were drawing them, but they're especially helpful for more advanced mathematics. A concave polygon is when any part of a diagonal contains points in the exterior of the polygon. It means that the polygon folds inwards. This thing about the diagonals, that would be like if I had a polygon like this. We notice it's concave because the sides on the right and left are going in. And then if I were to draw this diagonal, right, connecting those two vertices, you notice that that is on the outside of the polygon. If you have a a convex polygon, something that looks like this, anytime you connect two vertices, the line will always be completely in the interior of your polygon. Now, we do want to note that all regular polygons, using the definitions we've done above, are convex. And any polygon that is not regular is called irregular. And we can still do a lot of math with irregular polygons. We just have to make sure that we are understanding that the angles are not going to be congruent. Now, there are special names for polygons. You're probably familiar with most of these. We have a triangle for 3 sides, quadrilateral for 4, pentagon, hexagon. For 7 sides, the best term is a heptagon. You might see in some instances using a septagon, S-E-P-T. The reason we avoid this is the same reason we avoid undecagon for 11. It's just because you're mixing up Greek and Latin prefixes there, and that gets a little bit weird. So we prefer heptagon and hendecagon because those only use the Greek prefixes. Now, if we're talking about polygons with more than 12 sides, we normally don't use the words. We can make names with the words, you can look that up, but we normally just call it an n-gon, where n is the number of sides. So you could have a 24-gon or a 14-gon, and that's just telling us it is a polygon with that number of sides. If you ever forget any of these names for the smaller ones, you can also use that number of sides as well. So you could say a 10-gon, but you should be familiar with all of these terms. So those are the terms that we use to talk about polygons. Now, we do have 2 important formulas when we are talking about interior angles, and they are directly related to each other. So if we're going to start over here, where we're talking about the sum of the interior angles of a polygon. So we're talking about only the angles on the inside. And the sum of the measures of the interior angles of a convex polygon, we are specifically talking about convex polygons, is n minus 2 times 180, where n is the number of sides. We normally use that variable n to talk about some quantity that is an integer. So in this case, it's the number of sides. You're not going to have a fraction of a side. So to use this in example 1, they ask us to find the sum of the measures of the interior angles of a 23gon. Remember, 23 is going to be my value of n. So all I need to do to find the sum of the measures is substitute that into my formula. So I could substitute in 23 for n, and we get 23 minus 2 times 180. 180. 23 minus 2 is 21, so it's 21 times 180. And this is where I would take my calculator. So I could do 21 times 180, and we get 3780 degrees. So if we add up all of the angles in that 23gon, it would be 3,780 degrees. Now we can also use this to solve additional problems. In example 2, they give us a figure and they ask us specifically for measure of angle A. Now the first thing I'm going to notice in this problem is what type of polygon have they given me? They have given me a polygon with 1, 2, 3, 4, 5 sides. So I know n equals 5. I have a pentagon. I know that these two angles are 90 degrees. And then I know that I see that A and B both have arcs on them. That means they're congruent to each other. Just like when we were doing angles earlier in the year, when they have those arcs, that's telling us they're congruent, so I can label them both with the same variable. So the first thing that I'm going to do is I am going to figure out these total angle measures in this pentagon. So I'm going to use my formula, n minus 2 times 180, and I can substitute in 5, so we get 5 minus 2 times 180 is 3 times 180. And this can be where I take my calculator, and I can do 3 times 180, and we get 540. So I know that all together, they add up to 540 degrees. So I can add these three up. So this is 180 plus 122 is going to be 302. So we've got 302 degrees plus 2x equals 540. I got 302 by adding 122 plus 90 plus 90 gave me 302. So now I can solve this equation. I can subtract 302 on each side, and we get that 2x equals 238. Then I can divide by 2, and we get that x equals 119 degrees. So that is my value of A. So the first step in this problem was to find the entire angle measures of the pentagon, and then we could just add up the angles that they give us and use that to solve for the unknown angle. So that is using our sum of the interior angles of a polygon. There is another formula when we can adapt this formula to find each interior angle measure. The one thing to notice about this formula is this is specifically for a regular polygon. So to remind us of our definition, a regular polygon is convex, equilateral, and equiangular. So it means that the sides and the angles are congruent. And in a regular polygon, each interior angle measure is we could calculate that by taking the sum of the interior angle measures, that's n minus 2 times 180, and dividing it by the number of angles that we have, because we know all the angles are going to be the same. So this is our formula for each interior angle measure. N minus 2 times 180 divided by n. So we can adapt this or we can use this to solve a problem. What is the measure of each interior angle in a regular dodecagon? Notice here they wrote it out in a word, so I have to know that a dodecagon has 12 sides. Once I know that n is 12, I can substitute this into my formula. And we do 12 minus 2 times 180. And because I want each angle, I'm going to take that value and divide it by 12. This is equal to 10 times 180 divided by 12. And I can just take my calculator to solve this. Notice I am using the Desmos scientific calculator. I think it is very helpful for this. Then I am dividing by 12. And we get that each angle is 150 degrees. So that is the most direct way to use this formula, is they tell us the number of sides and we can substitute that in for n to get our angle measure. There is one more way to use this. In this case, they're giving us the angle measure of 135 and asking for the number of sides. They're asking for the value of n. So my formula would now be 135 equals n minus 2 times 180 divided by n. Because I know the angle measure and they're asking me for the number of sides. This is going to require a little bit of algebra. I'm going to start by getting this n out of the denominator by multiplying both sides by n. So these will cancel out, and we end up with 135n equals n minus 2 times 180. And then I could distribute n to both terms, or distribute 180 into these parentheses. So I get 135n equals 180n minus 360. Now this is a small equation with one variable in it, so we can solve it. I'm going to subtract 180n on both sides, and we get negative 45n equals negative 360. You also could have moved the 360 over and then subtracted 135 if you wanted positive numbers. And then I can divide both sides by negative 45, and we get that n equals, and this might be where I take my calculator, we have negative 360 divided by negative 45, it's not 45, and we get 8. So n, in this case, an octagon would have angle measures of 135 degrees. Now we could also check this by substituting it into the formula. If I substitute it in, I could do 8 minus 2 times 180 divided by 8. And if I check that on my calculator, I should get 135. So let's check that. So I'm going to set up my fraction, and we're going to do in parentheses 8 minus 2, close parentheses, times 180. And then we're going to divide that by 8. And you notice it does give us 135 degrees. So we have confirmed that this is the correct answer. And that is how you use the formulas for the sum of the interior angles of a polygon to solve problems. Thank you guys for watching.